Dear friends, today we will discuss some of the examples from numericals and exercise of chapter number 10. These examples are mostly related to interference phenomena. So now we will start with that illustration number 3, that is example number 3, illustration from textbook. And in that textbook on page number 366 it is given that two slits are made 1 millimeter apart and the screen is placed on 1 meter away. What is the fringe separation when blue-green light of wavelength 500 nanometer is used? So now in this question, if we go with the information as we had studied earlier, we can say that we are provided three different things. Here we can see that first we are given that slits are made 1 millimeter apart. So we are given this small d. Then it is given that the screen is placed 1 meter away. So we are also given capital D, that is the screen distance from slit, and then it is given that what is the fringe separation. So we are asked to find out this fringe separation beta when blue green light of wavelength 500 nanometer is used. So it is the lambda is also given. So now on the basis of that, as per as given information, we can apply this equation and get the answer from that. It is very clear that we can apply beta is equals to lambda d over small d. Here we are given all the important things that we are provided. Always write in this manner that what are given. So first it is given d, that is 1 millimeter apart. So it is given as 1 millimeter, that is 1 into 10 raised to minus 3 meter. Then d is given, that is 1 meter, and lambda is given, that is 500 nanometer. That means it is 500 into 10 raised to minus 9 meter, and that is 5 into 10 raised to minus 7 meter. So these are the three things that we are already given. So by using these three information, these three values, we can calculate the example now. So by putting lambda is equals to 5 into 10 raised to minus 7 into the value of d, that is 1 meter, and in denominator we can put, that is 1 into 10 raised to minus 3. So when we put the value, we get the answer as 5 into 10 raised to minus 4 meter, and that means it can be written as 0.5 into 10 raised to minus 3 meter, but as 10 raised to minus 3 meter can be written as a millimeter, we can have answer that beta is equals to 0.5 millimeter. So this is the illustration number 3 from the textbook. So this was the answer from the textbook illustration number 3. Now we will calculate some of the example from exercise. So on the basis of exercise, the examples are actually simple, and it also has some connection with the previous chapter, that is chapter number 9. So The first example from the exercise, it is given that monochromatic light of wavelength 589 nanometer. So we are given lambda 1. Here we will put all the things, that is 589 into 10 raised to minus 9 meter, because 1 nanometer is 10 raised to minus 9 meter, is incident from air on a water surface. What are the wavelength, frequency and speed of reflected and refracted light? That refractive index of water is also given, that we can use over here. That refractive index is indicated by n, somewhere it is also indicated by mu, and it is given as 1.33 for water. So we can write in this manner. Here for reflected light we can say the phenomena of reflection. So first answer we go for the reflected light. What we can write over here, we can say that since the speed of light in a given medium is fixed and the frequency of light does not change when it reflected from the surface, therefore its wavelength should also remain unchanged, and therefore the speed of light is equals to speed of light in air. So here first thing that we calculate, speed is equals to speed of light in air. So this is the same, it will be the same value that it is given, that is c is equals to 3 into 10 raised to 8 meter per second, that is known value. Now b, the wavelength will also remain the same. So wavelength lambda is also 589 nanometer, as it is in the air, because in the reflection it will not change. And now for the frequency, we can see that c is equals to lambda into frequency f. So frequency f can be written as c over lambda. C is 3 into 10 raised to 8 and lambda is given 589 into 10 raised to minus 9. So ultimately it will provide us the value 5.09 into 10 raised to 14 hertz. So this is the answer of the part for reflected light. Now for phenomena of refraction, as we go with the case for refracted light, so that is our case number 2 of the question. We can say for refracted light, what we can have, that frequency that is observed, we can simply write down over here that for the phenomena of refraction, the frequency remains unchanged, that is the both wavelength and speed will get changed here. So here first we will say that frequency will not change. So remain unchanged, and then wavelength and speed. So wavelength and speed may get affected. So for wavelength we can say that can be given, that is lambda in a water is equals to C by mu, where mu is a refractive index of water. So here we use mu W, and now we know the value, that is 3 into 10 raised to 8 divided by 1.33, that is equals to 2.26 into 10 raised to 8 meter, that is C lambda. So actually the value of speed, here we have written little bit wrong thing, that we have to first find the speed. So this is the formula for the speed. So velocity in water we can have, that is meter per second. Now using this velocities equation we can have v equals to lambda f. So that we can have the value of wavelength, that can be find out, that v is equals to lambda into f, where we have suggested and we have cleared that frequency will not change. So lambda of water, that is v of water upon f. Now v in water, that is obtained 2.26 into 10 raised to 8, and frequency, that is already been obtained 5.09 into 10 raised to 14. So this will be ultimately, that is wavelength in water will be about 444 into 10 raised to minus 9, and that is about 444 nanometer. So this will be your answer. So this is your exercise example number 1. Now in example number 2 they have asked a few terms that in the different cases how the shape of wavefront will be. So this is one just oral type of question and we have already discussed about it. So for the second number question it is given that light diverging from point source. So first case, when they have asked us the shape of wavefront, that we have to determine. From the question we can say the first part, the question is what will be the shape of wavefront when light diverging from point source. So the answer can be a simple, a point source is there, that means wavefront can be a spherical wavefront, because all such points which are equidistant from the point source will lie on a sphere. So first case the answer will be spherical, because source is point. So shape will be spherical. Now in the second case, it is given that light emerging out of a convex lens when a point source is placed at its focus. So obviously the again answer is very clear. The shape will be plane wavefront because light emerging from the convex lens as a parallel beam for which wavefront is plane. So here in a second case we can say that the shape will be plane. Here we determine shape and which type of source we are given. So here in second case it will be a plane wavefront and the source, that is a point source, was there in a previous case. Now here it is emerging from a convex lens. So due to emergence from convex lens, so the rays will be parallel and therefore the wavefront will be of plane type. Now example number 2's C part. The portion of the wavefront of light from distant star intercepted by the earth. So again the shape will be plane because the object is coming very far away. So because a small portion of a spherical wavefront of a very large radius is nearly planar. So it is a very clear thing that a small portion of a spherical wavefront is nearly planar body or planar. So this will be the considered as plane wavefront. So all these things, or in all these case the wavefront are given as the shape. Now we will move towards the example number 3. So in this example number 3 we are again provided a simple information that the refractive index of glass is given. So mu of glass is given here 1.5. So refractive index of glass is 1.5. What is the speed of light in glass? So it is very clear question. We are asked the speed of light in glass. So V is to be find out first question. Then speed of light in vacuum is given as a 3 into 10 raised to 8. So this is example number A. We are given C is equals to 3 into 10 raised to 8 meter per second. So we can simply say that mu is C over V and therefore V is C over mu, that is 3 into 10 raised to 8 divided by 1.5. So the answer is very clear, that is 2 into 10 raised to 8 meter per second. So this will be the speed of light in the glass material. Now the question is the speed of light in glass independent of color of light? If not, which of the two colors, that is red and violet, travel slower in a glass prism? So now again, as I have told you, that for the case of this type of question, we again have to move to the chapter number 9, in which we have studied that is the refractive index of violet color is greater than the refractive index of red, and obviously velocity is c upon mu. So when we are talking about the speed of light is not independent of color or wavelength of the light. The violet color travel slower than the red light in a glass prism, and the reason is very clear that refractive index for violet color is greater than the refractive index of red color. So the answer B of the same question will be no, and the reason is given over here. So this is the case of the example number 3. Now again the phenomena of interference is there with example number 4. So the example number 4 gives the information of interference pattern. How it is given, let us see that in a Young's double slit experiment, the slits are separated by 0.28 millimeter. So we are given here small d again. This small d is 0.28 millimeter. So this is 0.28 millimeter, that is 0.28 into 10 raised to minus 3 meter. So this will be the separation. Now the screen is placed 1.4 meter away. So the capital D is given, that is 1.4 meter away. So that is also given. The distance between the central bright fringe and the fourth bright fringe is measured to be 1.2 centimeter. So here that distance from central to the bright fringe is given, that I give as a name x4 on screen, that is given 1.2 centimeter, that is equals to, that is 1.2 into 10 raised to minus 2 meter. Determine the wavelength of light used in experiment. So we have to determine the wavelength over here. We follow the position of n bright fringe. We can say that xn is equals to n lambda d over small d, and on the basis of that we can simply say that for our fourth number screen we can put all the values, that is lambda d is given as 1.4 and small d is also 0.28. So we can have lambda is equals to x4, that is 1.2 into 10 raised to minus 2, then small d is given 0.28 into 10 raised to minus 3, then number 4 as a n, and d. So the d is given 1.4 meter, and ultimately when we put all these things together we get the answer 6 into 10 raised to minus 7 meter, that is about 6000 angstrom. So the answer is 6000 angstrom. So this is the answer, question number 4. Now we will move to the next question, that is example number 5. This is one of the IMP example from the textbook. So exercise example number 5, the information is given is like this. In Young's double slit experiment using monochromatic light of wavelength lambda, so the wavelength is used is lambda of monochromatic type of light. The intensity of light at a point on a screen where path difference is lambda is a k unit. So intensity, that is the resultant intensity, is given as a k units. And what is the intensity of light at a point where path difference is lambda by 3? So the intensity is k units when path difference is lambda. So we are asked that what will be new intensity when path difference is, उसको हम बताएंगे p से. So the path difference is, suppose p is lambda by 3. So we have to find out the intensity. We are given one information for the intensity part of view, that intensity is k units when path difference is lambda. Now when path difference is given as lambda by 3, what will be the intensity? So this is the question. Now to solve this question, what we will do, we can simply go with the information again. As we can say, the actual equation of intensity, we have two sources. So resultant I is given by, suppose, I1 plus I2 plus 2 under root I1 I2. So this is the condition for the given case. As we apply the equation, now consider I0 be the intensity of either source. That means both are of the same type of light sources, and then we can say that if we consider that I1 is equals to I2 is equals to I0, then we can say that I is equals to 2I0 plus 2, here it is I0 square cos phi. Now this will be ultimately 4I0 cos phi. Now this is the equation for the intensity. Now when we put this term as a condition, sorry, this is not the case, here we have put some wrong equation, here it is not in the multiplication. So this would be like 2I0 into 1 plus cos phi. This will be the resultant intensity I. Now from this information we can say that if we simplify the term of cos theta and we apply the equation, that is 2 cos square phi by 2 is equals to 1 plus cos phi, then we can have that but 1 plus cos phi is equals to 2 cos square phi by 2. So we can use this condition over here. So by applying this condition, we can have the equation of intensity is like I is equals to 2I0 into 2 cos square phi by 2, and therefore this is 4I0 cos square phi by 2. So this is the case. Now when we consider in a simple manner that path difference is lambda, so it is very clear that when path difference which is given, when path difference is lambda, that means if p is lambda, then obviously phi will be 2 pi, because in one wavelength the phase difference is 2 pi. So when it is the case, we can say the answer of the case will be, that is I is equals to 4I0 cos square 2 pi by 2, that is cos square pi, that is 1, and that means it will be only 4I0. So ultimately I is equals to 4I0, and that is given as a k. It is given that initially when path difference is lambda, then intensity is k units. So ultimately we can say that, so when path difference is lambda, intensity is equals to k, and it is equals to actually 4I0. So this is the case we can have. Now we go with the condition of path difference lambda by 3. So as the case, we are asked that when path difference is lambda by 3, then what will be the intensity I dash? This is our the question. So obviously when p is lambda by 3, so the phi will be, that is 2 pi by 3. So we can say that therefore the condition, that is p is lambda by 3, then phi will be, or phi dash will be, that is 2 pi upon 3. So when we put this value into the above equation, we can have, that is intensity I dash is equals to, that is 4I0 cos square, ultimately it will be pi by 3, because 2 will cancel out by that, and it will be, that is 4I0 into 1 by root 2 square, sorry, it is again 1 by 2, so that will be 1 by 2 pi by 3, cos pi by 3 is 1 by 2, so it is 1 by 2 square, that is 4I0 into 1 by 4, that will be ultimately I0. So here I dash is equals to I0. Now we have to compare it with the terms of k. So here we can say that I dash is equals to, if I want to write it in a term of k, then I dash over I is equals to I0 over 4I0. It is very clear that 4I0 itself is a k. So here it can be considered that if we go with the condition, that is I dash is equals to 1 by 4 I, but I is given here as a k, so I dash is equals to k by 4. So that will be the answer for the new intensity, that is k by 4. So this is the answer.